My name is Paulo. I'm an assistant professor here at the Department of Physics. That's my tenure home. And I have a joint appointment with the Department of Electrical and Computer Engineering. A little bit of background and state of affairs. So this is me. I'm here at Physical Sciences Building 436. My email, website. I have done my bachelor's and master's in computational physics at the University of São Paulo in Brazil. I also did my Ph.D. there with 1 year as an exchange period here in the US at sunny Buffalo. And from 2021 to 2024, I did my habilitation in condensed matter physics in Germany. And habilitation is essentially like a second Ph.D. that one could do, and that allows, that gives you the right to teach at German universities and also to advise students, even though you're not holding any particular permanent position in that university. In terms of mentoring, I am a member of the National Mentoring Community of the American Physical Society, where the goal is to match students with mentors, and particular students that are coming from backgrounds that are not traditional in physics or related areas. In terms of students here at UCF, I'm just arrived 1 month ago, and I'm currently interviewing PhD students and postdocs and aiming to start either in summer or fall. Since I'm also quite new, I did not take any teaching this semester so that I can organize my life here in the research group, but I am interested in teaching a variety of topics, including quantum mechanics, solid-state physics, computational physics, and semiconductor devices. In terms of research, I would categorize myself as being a theoretical condensed matter physicist with a strong overlap with material science. And as a subset on this very broad topic, I have been investigating a lot fundamental aspects of semiconductor physics, and I will show you why that is important. So semiconductors are the backbone of modern technology, and essentially they are in this very privileged spot because of how the electrons in these materials are occupying the energy levels. So for example, this is a scheme of the energy band in a semiconductor, and it tells us that the electrons fill out the band, and to reach the next available state, they have to go through the so-called band gap, which is essentially an energy barrier. You can take advantage of this and include some impurity levels, which would then facilitate transport. And this is actually the building block of transistors. And everybody's using a computer nowadays, and roughly the chip of the computer is half the size of the first transistor and has 3.2 billion transistors. This band gap can also be used for optics. So that means this energy barrier translates to the light, to the color of the light. And this is a fundamental ingredient for laser diodes and light emitting diodes that are being used throughout our devices. I just want to show some keywords here related to the research topics that I have been doing. One related to the kind of semiconductor systems. It ranges from 3D to 2D materials more recently. I have investigated different topics related to electronics, spin, and optical properties in these materials. I use on a daily basis several methodologies. I'm also showing them here. Maybe some of these keywords resonate with the research that you've been doing, and we could have further discussions on these topics. But today I would like to discuss exciton complexes in semiconducting van der Waals quantum matter. So this figure on the left essentially is the figure of the previous slide, where I'm showing that if you promote an electron from the valence band, this occupied states, to the conduction band, they will not be invisible to each other. In reality, they will start to interact, and this interaction will give the so-called excitons, which are these discrete states that have an energy below the band gap. So this energy is what we call the binding energy. And these excitons can also be interacting with other electrons in the system, and then we give different names to these new quasi-particles, and we call them trions. And this interaction is very strong and can be easily observed. And in any optical spectrum, here I'm showing the absorption, and the blue lines are what would be observed when you include this excitonic effect, so this interaction between electrons and the empty states. And the gray is if you had no exciton. And contrasting the 3D and the 2D case, the main effect of the dimensionality of the system is in the binding energy. So we have binding energies on the order of 10 to 20 millielectron volts for 3D systems, and 100 to 500 millielectron volts in 2D materials. And that means this is way above room temperature. So which means that excitonic systems are inherently brighter and could be used for novel devices. Van der Waals matter essentially means that the type of materials that we are talking about are composed of different layers, and within the layer we have in-plane covalent bonds, and the layers are coupled to each other by van der Waals interactions. So this material that I'm showing here is an example of transition metal like chalcogenide, or short for TMDCs, but this could also be, this is the same type of material of graphene, for example. And the quantum that I have in the title essentially means that these quantum materials depend on a very strong electronic correlations, and this could also give rise to new emergent order in these materials. And particularly to showcase that TMDCs and van der Waals materials are being used, or in modern technology, there are some device concepts that people have achieved in the past few years and have shown that you have LED operation or laser operation, particular to quantum information science. People have shown that you can build quantum emitters with these materials, and some more fancy architectures as the so-called exciton transistor. Under this umbrella of excitons and semiconducting van der Waals quantum matters, I would like to show you some of the research I have been doing in the past few years, and that I also plan to extend here at UCF, and that is related to magneto-optics of excitons. And that basically means we take this material, put it in a strong magnetic field, and investigate the excitonic spectrum. And basically, what we would observe is that you have two peaks of emission, one with polarization clockwise and the other one with counterclockwise. And I'm calling this E plus and E minus. And this is what typically this energy as function of magnetic field would look like. This is what experimentalists record in the lab. And if we take the energy difference, is what we call the Zeeman splitting. And it would be basically a straight line in a simple approximation, governed by this constant G that we need to find out for this specific material. If we add up the two branches of this energy dispersion, we see something that is proportional to the p squared, and this gives different insights into the kind of excitons that we have in the system. The main point that I would like to make here is that these G factors actually reveal very important physical properties and can be used as an imaging tool to understand fundamental interactions in these materials. For example, around 2015, people have measured this valley Zeeman splitting, the Zeeman splitting in this TMDC materials, and they do observe that it follows a straight line. They are able to extract this constant, but it took us roughly 5 years to really explain what's going on. And I'm just going to shine these expressions here to tell you that the main ingredient here is the orbital angular momentum, which takes this very complex form when you compare to just the spin angular momentum. But long story short, we implemented all these equations and revealed that these materials require very slow convergence. This is what this plot shows. But if this is done properly, the numbers that we get for the exciton G factors match very well with what they observed. And these are fully converged from first principles calculations, which is the kind of a theory that we are looking for, and it has a very strong prediction capabilities. I'm just going to show you a bit of what we have done. We have investigated structural deformations, and the main prediction is that it follows this trend here of being more negative as you increase strain and less negative and if you decrease strain, which helped us to understand a lot of experiments out there. For instance, in this example, the theory is above the experiment, and that's because the strain here is non-uniform. In this other example, we were able to reveal that what is really being measured is a hybrid exciton between two different species that live within this material, and that could only be done. And my claim is that this was only possible by using this imaging tool of the G factor that we were able to explain. We were able to make predictions for van der Waals heterostructures. So typically you can combine different 2D materials and then you find new exciton species where electrons and holes are delocalized in different layers. And with our calculations, we could really say, by combining magnetic and electric fields, what kind of exciton species you would be observing in the optical spectrum. For this other example where we combine these TMDCs with graphene, we were able to explain this very unusual non-monotonic feature that was experimentally observed. And that comes from the interlayer hybridization between these two materials. So really details of the microscopic interaction between the electrons in these two systems. And going beyond excitons, we have also explored how we can combine optics and transport in flat band materials, for instance, this indium selenide. And our calculations have provided fundamental insight into where these things are coming from and why the spin polarization is so small. There are many open questions in terms of fundamental aspects. There are things that we really do not understand. Regarding more towards applications that we still don't understand is why these things called ultra-fast pseudo-spin oscillations are oscillating so fast. What is the main physical mechanism behind that? And also what happens when we couple these materials with magnetic materials. So as a future plan, I would like to investigate this van der Waals quantum matter in more detail, particularly looking at these fundamentals of exciton complexes, expanding this to investigate dynamics, and also how these excitons interact with other quasi-particles, which would be an interesting ingredient for hybrid quantum information processing. And at the long term, I would like to really make modeling realistic devices. And for example, I give you this example of a spin laser, where there are many details of the basic ingredients that we could still investigate and that we need to investigate to really make a claim of how would be the best operation in this kind of devices. There are many opportunities for theoretical developments to grasp new fundamental insights into novel physical phenomena in these quantum materials, and also to collaborate in the fields of optoelectronics, optospintronics, and quantum information technology. I would like to thank all the collaborators that have been involved in this studies, and also the funding agencies, and you all for being here, and you can find me here at the Physical Sciences Building. Thank you very much.